Today, we're diving into a really cool breakthrough where chemistry and medicine are coming together in a big way. We're talking about using a pretty revolutionary material, basically a type of liquid salt, to build microscopic weapons that can actually hunt down and destroy cancer cells. This is where science gets personal.
I mean, just think about that for a second. Not some blunt instrument, but a weapon of absolutely incredible precision, put together atom by atom to target a disease right at its source. It definitely sounds like something out of a sci-fi movie, but it is way closer to reality than you might think. And to get there, we first have to solve a couple of huge problems.
So, before we get to the amazing solution, we really need to understand the two main challenges that scientists are wrestling with when they try to create these tiny weapons. First up is the problem of collateral damage. A lot of the cancer therapies we have now, while they're definitely powerful, are kind of like using a sledgehammer when you really need a scalpel. They can end up harming healthy cells right along with the cancerous ones. The dream has always been to be way more precise and a lot less destructive.
And here's the second and maybe less obvious problem: the manufacturing process itself. See, creating the tiny metal nanoparticles that you need for this kind of therapy, well, historically, it's relied on some really nasty chemicals. Get this, over half the materials used in making pharmaceuticals can just be solvent waste, which is often toxic and just terrible for the environment. So on the one hand, you've got the old way of doing things, these volatile organic compounds that are flammable, toxic, and just create a mess. And on the other hand, there's this clear, desperate need for a green alternative, a solvent that's safer, more stable, and doesn't leave behind a toxic headache. This is the big chemical puzzle that needed solving. And that brings us to the hero of our story, a strange, incredibly versatile, and really promising class of chemicals that just might be the answer to both of our problems. As the research says, scientists identified a new class of low-temperature molten salts as the perfect candidate. You might know them by their more common name, ionic liquids. And let me tell you, these things are a total game changer. So what on earth is an ionic liquid? Well, it's pretty much what it sounds like: salt that's liquid at or near room temperature. But the real magic is in its structure. It's made of these positive and negative ions that you can mix and match in countless combinations. That means you can literally design a solvent with the exact properties you need for a specific job. That's why they call them designer solvents. And the progress in this field has been incredibly fast. Ionic liquids went from just a scientific curiosity way back in 1914 to these highly tunable liquids in the 90s. And today, we're already on the third generation, super specific liquids designed for exactly this kind of work, like building cancer-fighting nanoparticles. Okay, so now we get to the really clever part: how these ionic liquids actually pull off their magic trick on the nanoscale. Right, how does this special liquid take a chaotic bunch of metal ions and somehow assemble them into perfectly formed, stable nanoparticles? It all comes down to control. The whole process basically happens in three key stages. First, the metal ions become neutral atoms. Simple enough. Second, these atoms start to clump together, forming the tiny core of a particle. And third, and this is the most important step, the ionic liquid swoops in and surrounds the particle, stabilizing it, and stopping it from growing out of control. The best way to think about it is like this: the ionic liquid is both a smart scaffold that guides the construction, and it's a molecular bodyguard that protects the finished product. It controls the final size and shape, and then it makes sure the particles don't all stick together and become one big, useless clump. So how does it stop the clumping? Well, it creates this awesome electrostatic shield. See, metal nanoparticles are naturally looking for electrons, so they attract the negatively charged ions from the liquid salt, and those stick to the surface. Then, the positively charged ions form an outer layer around that. So now you have all these particles with a positive outer charge, and they all repel each other. It's like trying to push the same ends of two magnets together. They just can't stick, which keeps them separate, tiny, and super effective. So, okay, we've got our nanoparticles. They're perfectly formed in a green solvent. But here's the million-dollar question: do they actually work? Let's take a look at what happens when they go head-to-head with cancer cells. The results are, frankly, incredible. Nanoparticles made of things like silver, gold, and yttrium oxide showed outstanding activity against HeLa cervical cancer cells. Others, using ytterbium oxide, had potent effects against MCF7 breast cancer cells. This isn't just a theory, folks. This is real, tangible success in the lab.
And what's even crazier is that the impact goes way beyond medicine. These exact same nanoparticles turn out to be powerful catalysts. That means they can speed up really important industrial reactions, like producing chemicals or fuels, making them faster and more efficient, all while using a much greener process. It's a win for industry and a huge win for the environment. Now, all of this is incredibly promising, but the journey from a lab discovery to a real-world clinic is, well, it's never simple. Let's look at the hurdles that still need to be cleared. There are really three main challenges ahead. First up is cost. Ionic liquids can be pretty expensive, so figuring out how to recycle them efficiently is absolutely key. And, of course, the most important step of all, we need to prove this works safely in living organisms, not just in a petri dish. That is the next great frontier for this research.
It really just leaves you with this one final big thought. We are learning to build tools on a molecular scale, with a level of precision we've never ever had before. Fighting cancer might just be the beginning. The real question is, with technology this powerful, what other impossible problems are we going to solve next?